What's up, nerds? So today I want to talk about slope fields. So slope field is useful for when you might not know the solution to a differential equation. You could still get an idea of how it behaves. So let's get started with an example. So our first example will be one that we probably can solve from regular old integral calculus tools. We'll look at y prime equal to t. Now, the way this works is first our axes are t and y. Okay, so pay close attention to that. And then at each point, t comma y, we're going to draw a little dash whose slope is given by the differential equation. So if t comma y equals 1, 1, then our slope in this case is just t, which is 1. So at 1 comma 1, we draw a little dash with the slope of 1. So while doing this, we might notice that for any t equals 1, y prime is going to be 1. So along the whole line t equals 1, the slope should be 1. And this holds for other t values. So when t is 0, the derivative is 0. So we could go along the y-axis drawing little dashes with slope 0. And we could continue to do this for different t values. Maybe t equals -1, and then t equals 2 and 3, or t equals -2 and -3. And after a little bit of time, we'll know what the slope is for pretty much all values of t and y. Our picture agrees with what we would expect because the solution to this DiffEq is y of t equals t squared over 2 plus c, parabolas. So it looks like if we put in an initial conditions like y of 0 equals 2, put our marker at 0, 2, and then just draw where the slope field tells us to go, we'll get a parabola. And same thing with if we start at another point. Say, if we start at 1, -1, we'll also get another parabola there. Okay, so that's our first example. Let's take a look at a slightly harder one whose solution we might not know immediately. So look at y prime equals y. And again, draw our axes t and y. And look at the point 0, 1. And we get this, the slope is 1 there. So at 0, 1, we draw a little dash at 1. And we notice immediately that for all values y equal to 1, we get that the slope is equal to 1. So now, on that line, we could draw dashes with slope 1. And this holds for other y values too. So when y is 0, the slope is 0. And that actually gives us a solution to the differential equation. So y t equals 0, if we plug that into the differential equation, the derivative is 0, we get y prime equals y. So that's what it means to solve the differential equation. The whole equation holds. So we could continue drawing our slope fields. Maybe draw a y equals 2, or y equals 3, y equals -2, -3, -1. We draw all the slopes there, and maybe plug in some initial conditions like y of 0 equals 1, and then see how that behaves going forward and backwards in time. Or something like y of 2 equals -1, and in both cases we get exponential functions, and that agrees with the answer. Y of t equals ae to the t is the general solution to this differential equation. So all of our solutions are going to look like exponentials. Okay, let's look at another example. This time y prime equals t plus y. So if we look at 1, 1, slope should be 2. So at 1, 1, we draw a dash of slope 2. And maybe let's try another point. So if we do t equals 0 and y equals 1, then we get the derivative is 1. So we draw a slope of 1 there. And in general, on the line y equals 1 minus t, if we plug that into the differential equation, we get that the slope is 1. So here's the line y equals 1 minus t. Along that line, the slope is always 1. And then on the line 2 minus t, the slope is always equal to 2. So we could draw dashes of slope 2 on that line. And on other lines like y equals -t, or y equals -1 minus t, or y equals -2 minus t, the derivative is constant. So we could fill in our slope field pretty easily by looking at those lines. And we see immediately y equals -1 minus t as a solution, and that should be an exercise. You should just plug in that into the differential equation and see that it actually holds. So now let's look at some initial conditions. So y of 0 equals 2. Plug in the points, and the brown will be y of -1 equals -1. And the general solution is y of t equals -1 minus t plus ae to the t. So it's an exponential function as t. You could think as when t goes really big in the positive direction, it looks like an exponential function. When t is really big in the negative direction, it looks linear. Looks like the line 1 minus t. Okay, so now let's look at a fourth example, y prime equals t times y. And let's adopt the strategy that we did last time, where we take a constant slope and look at what values of t and y give us that constant slope. So if y prime equals 1, we have y equals 1 minus t, which gives us a hyperbola. So everywhere on the curve, y equals 1 minus t, the slope is equal to 1. So we'll get the positive and negative values. If y prime equals 0, that tells us that t times y is 0, so either y is equal to 0 or t is equal to 0. So on both axes, the slope is going to be 0. And you can see that that gives us a solution to this differential equation, y of t equal to 0, the constant function. That solves this differential equation. You can get 0 on both sides. We could continue by saying, well, if y prime equals 2, we get y equals 2 over t. Or if y prime equals -1, we get y equals -1 over t. And so on and so forth. Start to fill in our slope field. And to look at a particular solution, if y of 0 equals 1, you can see this is an even looking function. Goes off to positive infinity in both directions. And the solution to this is y of t equals ae to the t squared over 2. So when t gets really big, if a is positive, it's going to go to positive infinity. If a is negative, when t gets big, it's going to go to negative infinity. Okay, let's do two more. This time, y prime is going to be y times 1 minus y. And we could see whenever you have y prime equal to a polynomial of y, then the roots of that polynomial, in this case 0 and 1, are going to be solutions. So the constant function y equals 0 is a solution because both sides of the equation are 0. And same with y equals 1. Both sides of this equation are 0 for both those constant functions. Now for y bigger than 1, 1 minus y is negative. So the product, which gives us the derivative, is going to be negative. So everywhere above the line y equals 1 has negative slope. So we could just fill that in. And for y in between 0 and 1, both terms y and 1 minus y are positive. So y prime should be positive. So our derivative is positive. We could fill in that area between y equals 0 and 1. And then for the last region, when y is less than 0, then 1 minus y is still positive. So it's positive times a negative, and we get that that's negative, so the slope should be negative when y is negative. So another quick way to fill out your slope field. You could, in these instances, we call y equals 0 an unstable solution, aka a source, and y equals 1 is a stable solution, which is a sink. And the reason why we call them these is because if you go a little bit away from, say, y equals 0, like if y equals 0.1, then you're going to go really far away. You're going to diverge from it. So even though y equals 0 is an equilibrium solution, and you start at y equals 0, you'll stay there. You could think of it as putting a ball on top of a hill, where like it might be balanced there, but if it goes a little bit in either direction, it's going to go really far away. It's going to roll away. So y equals 0.1 will go really far away from y equals 0. But on the other hand, y equals 1 is a stable solution. It's aka a sink. So if we're between 0 or positive infinity, all those values, as time gets bigger and bigger, they're going to converge to y equals 1. And you can think of y equals 1 as the bottom of a hill, where if the ball's there, it's going to stay there. But even if the ball's a little bit further away, it's going to roll towards the bottom of the hill. So those are two different types of equilibrium solutions. We'll see them pretty often. Let's do another example where y prime is a polynomial. In this case, y prime equals y squared times y squared minus 4. And so the roots of that polynomial are 0, 2, and negative 2, which are all solutions. So y equals 0 is a solution to this differential equation. Y equals 2, that constant function, is another solution. And y equals negative 2 is a third solution. And now let's analyze what happens in between in all these different regions. So when y is bigger than 2, the derivative is positive. When y is between 0 and 2, the y squared is positive, but the y squared minus 4 is negative, so our slopes are negative there. And the region between negative 2 and 0, same situation, and the slope is still negative. Y prime is negative. And in the last region, when y is less than negative 2, y squared minus 4 is positive and y squared is positive, so all of those slopes are positive. By looking at this, you could see that y equals 0 doesn't look like any of the solutions from the last example. In this case, y equals 2 is a sink, it's an unstable solution. Y equals negative 2 is a source, it's a stable solution. Y equals 0 is what we would call a semi-stable solution, because, well, anything to one side of it, when y is between 0 and 2, the solution is going to come back down to it, and everything less than 0 is going to go away from it. So it's sort of like a sink on one side, sort of like a source on the other. So that's it for today. Hope you enjoyed the video. If you did, be sure to leave a comment, smash that like button, and subscribe, and stay tuned for more differential equations videos.